Good afternoon, everybody. Welcome to Organic Chemistry 2. We're going to continue our exploration of amines. And we already looked at nomenclature last day, and now we're going to get into reactions. And this being our last chapter of new functional groups, we're going to be reviewing all the old reactions we learned how to make amines already. And we're spending some time with this because all of those reactions we learned in the past are very important, especially as we progress in our discussion of amines. So let's get rid of our cute heading there and focus on the task at hand. Let's start over here. We're starting with a primary alcohol. In section 10.5, we learned that you could treat an alcohol with a strong acid, either sulfuric acid or toluene sulfonic acid, and heat, and cause what we called a dehydration reaction. Dehydration is a form of elimination that's very specific. You're eliminating water, and that creates an alkene. Alkenes can be easily converted to epoxides using molecules like meta-chloroperbenzoic acid. At this time, it's appropriate to review things like meta-chloroperbenzoic acid, since that chapter with aromatics is also on our exam. MCPBA. We have a benzoic acid that would have a carboxylic right there, but it's a per acid. That's the P. So it's OOH. And in the meta position, we have a chlorine. Meta-chloroperbenzoic acid. And there we have it. And it makes an epoxide from an alkene. Epoxides can be opened with a nucleophile, either of the moderate variety, as we see here, or a strong variety, and we would get the same result, an attack on the least hindered position, which is here. This is more hindered. And we have an amine opening up the epoxide. Initially, you get an ammonium ion down here and an alkoxide anion up here. The laws of pKa dictate that you must protonate the oxide and deprotonate the ammonium ion, and it happens in the same molecule because they can reach. And we have what's called a beta hydroxy. Beta hydroxy amine. Beta hydroxyamines are useful. They've got two functional groups. If we started with the same alcohol and reacted it with PCC, as we learned in chapter 10, we could make an aldehyde. And then aldehydes can be reacted with either a primary amine or a secondary amine, both in the same section of chapter 16. We're taking you back to the first part of this course. And if you do a secondary amine, you make an enamine. Enamines are easily reduced under these conditions, or a little reminder, these two conditions over here would work as well with a single star. Good little review page here. I'm pretty sure you have to agree. And we get an alkene to become an alkane, and that makes this an amine, a tertiary amine. And since we're in the amine chapter, let's review all the amines we're making here. We have a secondary amine here, and we made a tertiary amine here. And if we reacted the aldehyde with a primary amine, you get an imine here, imine. And then you can reduce that under the same conditions that we reduced this. And we make a amine here, and this time it is secondary. And there you have that. And what else? We've explored the left side going downwards. Let's look at going to the right. PBr3 is going to create an alkyl bromide where you used to have the alcohol. Very reliable reaction. We've used it on every test. And then you have a primary carbon with a leaving group. Take you back, way back. Primary RX. Strong nucleophile. When you're in chapter 9, you did analysis of these reactions, where you looked at the carbon with the leaving group, you looked at the nucleophile, and you looked at the solvent. Polar aprotic solvent. All of those lead to the conclusion of an SN2 reaction. SN2. And we make a new molecule. We learned that's called a nitrile in our last 2 chapters ago. Nitrile with one more carbon than the original alkyl halide. Where did the new carbon come from? Cyanide. And we can reduce that under the same conditions we reduced our enamine and our imine. And now our nitrile, same conditions, will make an amine. And this will always be a primary amine, because the carbon in the cyanide always gets 2 new H's, and the nitrogen also gets 2 new H's, and you have a primary amine. Very nice. I think we've explored all the avenues that lead from this starting material. There must be a restart somewhere, and I see it. It's right here. We have an aldehyde. We learned in chapter 16, if you react those with hydrogen cyanide, you make what's called a cyanohydrin. Cyanohydrin. That's a C. Hydrin. Hydrins are alcohols. We learned that in Organic 1. And that's an O. It's bothering me. And what's going to happen to our cyanohydrin? We're going to hit it with the same reduction we did with this nitrile, because this also is a nitrile. And we achieved the same result, a primary amine, but this one is beta to an alcohol, much like this one was. Beta, that's a beta hydroxyamine. You can name it that way or talk about it that way. Or you could say it's a beta amino alcohol, in which case you'd say the alcohol alpha is here and beta is there. All depends on your reference point, doesn't it? So we have a primary amine. Very nice. We could also oxidize this more fully to an acid of the carboxylic variety. That's what step 1 would create. And then step 2, an acid halide. Acid halides we can do a few things with. We can react them with an amine and make an amide. If you choose ammonia as your quote unquote amine, it's not really an amine, but it has the same chemistry. It creates a primary amide. And I want to remind you, in the Hoffman rearrangement, we lose the carbonyl. The carbonyl is gone, and we have lost a carbon and made a primary amine. So lots of amines. We didn't know we had all these reactions to make amines already in our possession. You could have taken the acid halide and reacted it with an aromatic species. I chose the simplest here, benzene. You need an aluminum chloride catalyst we saw last chapter to put the acyl group. And the reaction was called Friedel-Crafts acylation. I'm not too concerned about the two gentlemen's names, although they were fine chemists. Crafts acylation. Remember, an acyl group is a carbonyl containing species, and it's a new group right here on your benzene. So it's acylated benzene with a ketone. And then you can put a nitro group. Where's your nitro group going to go on this benzene? Well, what kind of a director is a partially positive carbon? It's a meta director, so that's why the nitro's in the meta position. And then we had several reactions that could reduce nitro to NH2, and we know they are all very important. So we're going to learn them all. And apparently I did some erasing up there, unbeknownst to me. Lithium aluminum hydride followed by HCl would also work. Hydrogen and nickel, tin and HCl, iron and HCl. They all do this job fairly well. But I shouldn't have included this entry here for this specific reaction. I included all the reactions that will make an NO2 into an NH2. In this particular one, don't use alternative number 1 because alternative number 1, lithium aluminum hydride and HCl, will make this into an alcohol. So we have a small mistake in our textbook, which is still in progress. So you can use this option or these 3 at the bottom, but please don't use this top one as an alternate here. And have we covered everything on this page yet? I think we have. Hydrogen cyanide. We ran around here. Yes. Now let's see if we can put it to use over here. I have the same corresponding numbers for creating this kind of an amine here. Would be amine number 1, I called it, and I want you to use a similar protocol to make this one, to make this amine here. So what did we do going from here all the way here? We made an alkyl halide, and then we made a cyanide, and then we reduced it. And in the spirit of doing thorough review, it doesn't have to be a bromine I put on there. It could be a chlorine. So in this example, I'll start with a chlorination. SOCl2 and pyridine would convert my alcohol to a chlorine. And I could do my cyanide reaction from there. KCN, maybe acetone is a different polar aprotic solvent. And in this example, I'd have to be a little more careful about choice of solvent because a secondary carbon with a chlorine on it's going to be a lot slower than the primary carbon with the chlorine. And I have to make sure the SN2 is the reaction that happens. So very important to choose the right solvent there. So we're at the cyanide stage. So at the equivalent stage of having a cyanide, and now we have to make it an amine. And we used H2PT, but we had options. Why don't we exercise one of those options right now? We can use sodium borohydride followed by HCl. NaBH4 followed by HCl. And now I'm going to use the approach that I used to make amine number 2 here. What was the approach? Well, we started with an alcohol. We're starting with an alcohol. We're oxidizing it to a carbonyl. In this case, it won't be an aldehyde. It'll be a ketone. Here's an aldehyde. And the ketone can also make an imine, or in this case here, because this is tertiary, we're going to go through by way of the enamine. And then we're going to reduce it there, maybe use our lithium aluminum hydride alternative up here. So what is the process? Got to oxidize to a ketone. You could waste some money on PCC. I don't have any objections. But with a secondary alcohol, you don't have to be so careful. You're not worried about a carboxylic acid. Instead, you could use your cheaper, much cheaper, by the way, potassium dichromate, sulfuric acid, water combination. That's the chromic acid conditions. We'll make a ketone from a secondary alcohol. That's chapter 10. We're at the ketone stage instead of the aldehyde stage. Really doesn't change things. Aldehydes and ketones have similar reaction profiles. We need to go to a tertiary amine, so we're going to hit it with a secondary amine. Make sure you use the right one here. Our secondary amine has to have an ethyl and a methyl on it. So here we go. HNET with a CH3 as well. Make sure it goes well with a Dean Stark trap. That's a D, not a P. because it's a condensation reaction. So now you're at the amine stage, and you need to reduce it. And we said we wanted to try the lithium aluminum hydride reduction this time. Well, I do want to point out that H2 and PT is a bad option both here and previously. If we used H2 and PT, what would happen to this here? Uh-oh, we'd reduce that. So H2PT is a bad choice for either 1 or 2 here. We have to worry about other functional groups being reacted when we don't want them to. Oh, I skipped step 3. You're going to forgive me? All right, 1, 2, 4, 5. It's like a Monty Python sketch. All right. So now we have a tertiary amine from our secondary, or from our ketone. Originally, it was a secondary alcohol, but we made it into a ketone. Then we make it an enamine here and reduce it. And there you go. Molecule 3 protocol started with an aldehyde to make a nitrile. Could have been a ketone that also makes a nitrile attached to an alcohol carbon, which is a cyanohydrin. And I believe in our process here, that's what we want. Well, wait a minute, we're starting here. This is going to be the same as up here. If you look carefully, you have a secondary cyanohydrin, and here, this came from a secondary cyanohydrin if that was a cyanide. So we can't do the cyanohydrin formation from an ester. That's what this is over here. Esters cannot make cyanohydrins. We have to convert it to an aldehyde first. So rack your brain on that one for a second. How do you make an ester into an aldehyde? We only learned one reaction that made any carboxylic acid derivative into an aldehyde, and it was an ester. There, that's merciful right there. And it was dibal, diisobutyl aluminum hydride, dibal H. And you follow that with HCl, and you have an aldehyde. And so you are at the stage where you started on the restart here. What did I do here to make a cyanohydrin? HCN. Here's our step 3. HCN. Now you have a cyanohydrin. I need it to become, there's cyano, used to be a cyano on this carbon. Now it needs to have 2 H's. Reduce here. And we're not worried about reducing anything up here this time. So we can use our H2 and PT to finish this one off. Although we had these 2 options as well up here. H2 and PT is a lot less writing. Sometimes we like that. Okay. So we've here in a dead end. That's why I put this blue box here. So you know this is not related to going to 4. This is going to go to 4 through 4 to get to this, sorry. Oh, that's an amine with 1 less carbon than this. Here was an amine with 1 less carbon than this. What was this? This is a primary amide. You can't do the Hoffman rearrangement unless you have a primary amide. So our new question is, how do you make an ester into a primary amide? The good news is any carboxylic acid derivative above an amide already will react with ammonia to make a primary amide. Wow, what did he just say? What I'm saying is the top 3 carboxylic acid derivatives in terms of their reactivity, that would be acid halides, acid anhydrides, and esters. Why did I get excited with esters? This is an ester. Will react with ammonia to make a primary amide. Yep, we're getting near the end of the semester. We got this big review, the most important review we've done so far. Oh, I found out how to get a button to the top of the menu. Learning every day. Okay. So I have a primary amide that I have to make undergo Hoffman rearrangement now. I'm currently at this stage in this sequence here. So bromine hydroxide XSAQ, step 2. Br2 NaOH XSAQ. And mission accomplished. Primary amide with one less carbon. Amine, sorry, primary amine with one less carbon. And that's the end of this and this. So now we're going down here. Oh, how do I make an ester into an acid halide? This is not about amines yet. That's an acid halide, in case you didn't see that. That's a carbonyl oxygen there. Acid halide. We only know one way to make acid halides in this course. There's an E that's not going to be an E no matter what I do. We only make acid halides from carboxylic acids. And how do you make a carboxylic acid from an ester? That's called hydrolysis. You can do hydrolysis under acidic conditions. I'll give it to you. It's not the best way for esters, but you can make it happen. You boil it up in like a 3 molar solution of sulfuric acid, and it'll become a carboxylic acid. And then step 2. Step 2, treat it with SOCl2 and pyridine. That's twice we've seen that on this review. SOCl2 and pyridine is good for converting alcohols. This alcohol here, secondary to a alkyl chloride, or converting a carboxylic acid to an acid chloride. And there's your acid chloride. How do I make that into a group on benzene? Well, there's a benzene. There's a ketone on benzene. It came from an acid halide. So 2 of the pieces are the benzene and the acid halide. And the third piece, which I wrote over a little bit, is the aluminum chloride catalyst. So we have an aluminum chloride catalyst and benzene. Yeah. There. And that gets us here. And then what's going on here? Oh, we're doing another version of 6 here. Or we didn't do a 6 yet. We did an amine, didn't we? Which number was the amine one? Amine? That was a 2. Yeah, we made an amine here. No, it was an amine. That wasn't a 2. That was a 6 as well. The concept is the same, though, whether it's going from an enamine or an imine. And we're doing another 6. We're going to make a tertiary amine from a ketone, just like we made a tertiary amine. Where's our 6? Tertiary amine from an aldehyde. We had to make an enamine first. So enamines using a secondary amine and a Dean-Stark trap. Ooh, there's our amine that's new on this thing. So that had an H on it. If you're curious, I didn't draw that to my liking. If you're curious, that amine is called Pipyridine. And yes, its name suggests something like it might be found in pepper, and you are correct. One of the peppery flavors of pepper is a pipyridine. And pipyridine is going to make an enamine. And what do we do with the enamine to make it into an amine? And you're going to say, wait, you forgot to separate it into steps. In truth, you don't have to separate this to steps. You can have all 4 of these chemicals together, the ketone, the secondary amine, the catalyst, and the hydrogen, and you will get a very nice yield of this amine. And it's a very clean reaction too. You just have to filter away your catalyst and the hydrogen's gone. It's a gas, just let it evaporate. And finishing, we got to finish up. This has been a long segment. That's okay. What's going on here? I'm taking the aromatic ring, and on the meta position, I have a new amine. Why meta? Because we had a ketone. Ketone, next group's going meta. What is the next group? Are you going to claim to be the first person ever that knows how to put an amine directly on an aromatic ring? Don't do that. That universe is not our current universe. What do you have to do to get an amine on benzene? Well, first you have to put a nitro on benzene and then reduce it without reducing the ketone. Remember my caution about don't use lithium aluminum hydride followed by HCl. All right, so first nitro group on benzene, getting ahead of ourselves. HNO3 and sulfuric acid. You got a nitro group on your benzene. Now I have to reduce it to a amino. And I'm going to use I haven't used the iron catalyst yet. Iron filings, they're called. The name says how they're made. You take a piece of iron and a nice metal file and you rub them together, and the filings that come off are iron powder or filings with a lot of surface area. And you have an amine on your benzene. We call that an aniline, don't we, right there? It's an aniline with a group on it. And finishing up, oh, we got a question? Maybe, yes.
Yes, Professor. So I'm just curious. You said we can use H2 nickel to reduce the nitro group into an NH2,
Sure, you
right?
could have used H2 and nickel down here. That would have worked just fine. This option right here.
Right. So my question is, since we have an aromatic group, the benzene, it's all double bonds, like it's an alkenes between like double bond between C and C.
Yes.
Wouldn't that affect, the double bonds inside the benzene?
Are you forgetting there's 158 kilojoules per mole of stabilization energy of the benzene pi bonds?
Okay.
They do not
Yeah,
reduce
I
under
did
normal
forget.
conditions at all. No, they are very hard to reduce. You need 200 atmospheres of pressure, and then you'll get H2 and nickel to do that.
Okay.
Okay.
Thank you.
You're welcome. Good question. And so we have our amine on our meta position. And now I need to have something that puts 2 groups on this alkene here. 2 groups. Then amine is on the less substituted carbon and an alcohol on the more substituted carbon. Oh, wait, I'm thinking epoxides immediately. Epoxides, if I have a triangle there, a nucleophile will attack from the backside the less hindered carbon, which is this one. Oh, look at the amine on the less hindered position. And the O anti to it because there was a backside attack. This is just tailor-made for epoxide chemistry. So how do you make an epoxide? Well, we could use MCPBA, but we already have that on the page. In our approach to our number 7, we're going to use MMPP, which is both safer and a little more environmentally friendly. So MMPP, PP, magnesium monoperoxyphthalate, fancy. And we can open that up with our secondary amine, or sorry, our primary amine, NH2 boo. I'll draw the boo. It's a butyl. And you're saying, wait, where does the alcohol get the H from? Well, the alcohol gets the H from this molecule. After the opening of the epoxide, you have an ammonium ion with a pKa of 10 and an alkoxide, an O- over here, will be a pKa of 17 if you put the proton on it. And yep, you've got to transfer from 10 towards 17. The rules of pKa must be obeyed, and they would be here. And that brings to close our longish first segment. We will pick up after the break with more reactions that make amines, ones that you may have not seen before. So I will see you then. Adios.